Hello everybody, my name is Paul Fidler and I'm going to talk to you about the long-term performance monitoring of Staffordshire railway bridges. This has been quite a long-term CSIC project and I'm going to talk to you about what we've done so far, and my colleague Dr. Farhad Huseynov will talk to you about where we're going from here on. For a bit of background, we can actually trace the origin of this project all the way back to November 2013 when we had a fibre-optic industry partner meeting, and at that meeting Dr. Mohammed Al-Shafi and Phil Keenan, our business development manager, pitched a potential project for CSIC Tranche 2 to use fibre-optic sensors, specifically FPG sensors, to look at dynamic structures, and the ones they were looking at were wind turbines and the foundations of wind turbines. Mohammed was very much a soil mechanics person at that point, but recognising that none of our industry partners actually had any wind turbines, they were willing to use pretty much any other structure to demonstrate the use of dynamic fibre-optic sensing. And as a result of that meeting, we learned that Network Rail were building 10 new bridges, railway bridges, in Staffordshire area as part of a rail congestion improvement project. This was the Stafford Area Improvement Project. The Staffordshire Alliance consisted of Atkins, who designed the bridges, Lang O'Rourke, who built all the components for the bridges and built the bridges on site. They tried to do as much off-site construction as possible. Network Rail were the ultimate client, but were also involved in the alliance, and Volker Rail basically install the track and the signalling and make the whole thing into a railway after everyone else has done their thing. And so this became the Staffordshire Bridges project, and Mohammed's initial goal was to track the entire load path through the structure, from the wheel rail interface through the rails, the sleepers, into the ballast, the deck, the beams, the abutments, and then ultimately all the way to the foundations. This is obviously quite a lofty ambition, and we eventually settled on instrumenting 3 sleepers per bridge. I think the poured concrete deck is instrumented on one of them, and several of the beams are instrumented with fibre grating sensors. And we were able to employ Liam Butler and Neve Gibbons. So Liam on the left and Neve on the right. So Liam came to us from Canada, Neve from Ireland, and we also had 2 visiting colleagues from China, Jinlong Zhu, who is a fibre-optic sensing specialist, and He Ping, who was from Tongji University. Jinlong was from Harbin, I should have said, and He Ping was from Tongji University in Shanghai, and he was a geotechnical engineer. So this is one of the 2 bridges. This is intersection bridge 5, otherwise known as Norton Bridge. It's an intersection bridge because it carries rail over rail. So in this case it carries a 2-line flyover over the fast 4-line track. So this is to avoid slow trains having to slow down fast trains when they were trying to go to the opposite rail. And this was originally constructed off to the side and then lowered into place, and then the concrete deck poured in place. So we had the opportunity to instrument it whilst it was off to the side, and then be very careful with the fibre optic cables as they poured the concrete deck. And just to the side of that, quite an orange tent, you can see a cabinet, which is where all the cables end up. This is under Bridge 11, otherwise known as Chepsey Bridge, and this is, you can see here that all of these concrete components are very high quality. They were made at Lang O'Rourke's Explore facility at Steatley, and just brought on the back of a lorry and lowered into place. And so the only part of this bridge that was done in situ is the poured concrete deck. The goal of this project was ultimately to demonstrate the feasibility of installing fibre sensors and demonstrating their usefulness, and achieving what Mohammed described as a sort of nervous system for the structure from day one of its life. And in fact before that, because we were able to monitor the stress in the beams as the pre-stressing was removed at the Steatley plant, for example. And so yes, it's a bit tricky, and you do need to be careful where your cables are going on site, but it is possible. And there was a lot of interest from Network Rail, so here is Neve holding court, explaining to lots of Network Rail visitors how the instrumentation works. And Network Rail support going forward would be very important. I should also mention that Cemex made some sleepers for us with fibre optic sensors built in, and these were tested non-destructively at Heriot Watt up in Scotland. That brings us on to the phase 2 of the project, and at this point Neve went off to manage the Future Infrastructure Built Environment Centre for Doctoral Training, and Liam very keen to continue working on the bridges, and Network Rail were keen on it too, and they actually funded the purchase of 2 fibre optic analyzers and multiplexers to be permanently installed on these bridges, and the goal was to have a 24/7 monitoring system, which didn't quite manage because it required a 24/7 power supply. We're also working with researchers, data scientists at the Data-Centric Engineering group at the Alan Turing Institute. They were looking for data sets, any data sets to look at, and so we were in the process of getting a data set. Because we didn't have a 24/7 monitoring system, Liam went with various people, volunteered to go and collect data on a monthly basis. So this is Liam on one of his monthly trips. I think this is the one I went on. And it's just a case of taking all the cables out of the cabinet and plugging them in, and it's very easy because the yellow wire connects to the yellow wire, which connects to the yellow wire. No problems there. And we were able to get monthly data sets. The weather was not always kind. This is an example of the sort of thing you can do with the data, so we've used this video at a few open days now. And the other thing we did with this data was we gave some of it to one of our RAs, Manuel de Villa, and he put together a sort of demonstration dashboard using Unity, which is actually a game engine. So this was able to give you a 3D view of the bridge. It's not really a digital twin, it's more of a example of a digital visualization. But this was used as the basis for some of the work Miguel has done with a digital twin, and you'll see some of the similarities later on. Liam has a very good talk on working with data scientists and the fact that they speak a different language to structural engineers, and I thoroughly recommend you look it up on our YouTube channel and have a look. And that brings us to Staffordshire Project Phase 3. At this point, Liam had left to go to a lectureship in York University in Toronto, but the Centre for Digital Built Britain was looking for some projects and had some funding available, and we applied. Basically to continue the goal of a 24/7 monitoring system and fitting in with Centre for Digital Built Britain's goals, make a full digital twin. And because this is the Centre for Digital Built Britain, I'm obliged to show you these two slides at this point, just to point out that the funding from CDBB comes from the Construction Industry Hub, which ultimately comes from the Government's Industrial Strategy Fund, and with that I shall hand over to my colleague Dr. Farhad Huseynov, who will tell you where this project is going forward.
Thank you, Paul. Hello everybody, my name is Farhad Huseynov. I'm a bridge engineer. I work as a senior research associate at CSIC, and I'm leading the current phase of this ongoing project. The main objective of this phase is to build a continuous monitoring system and showcase the practical application of bridge SHM integrated with digital twins to quantify the performance of the Staffordshire bridges. Previously, there was no power supply at the bridge site, so we collected data during short site visits. However, Network Rail has recently installed a permanent power, and we are currently building a system to acquire continuous monitoring data. The digital twin system we are developing has two main components for performing structural analysis and condition assessment. Broadly speaking, these are built-in processing algorithms and the 3D calibrated FE model. The post-processing algorithms will extract useful information from the monitoring data that will be later fed into the FE model to provide information such as load effects and deformations, basically parameter of any interest everywhere on the structure. So the connection between the real and the digital twin is the key aspect of the system. It was one of the main challenges that we needed to address at the beginning, how to connect the digital twin to the physical one so that it represents the real conditions occurring at the site. So the input parameters basically needed to be obtained accurately. However, bridges are dynamic structures, as you know. Traffic loading is highly variable. Also, although these bridges are designed as simply supported structures, past studies have shown that the boundary conditions has a significant effect on their structural behavior. But traffic loading at the bridge site can be obtained using a bridgeway motion system that uses the deformation response of a bridge to a passing vehicle to back calculate its axle weights. In addition to deformation sensors, bridge WIM also requires an axle detection system. Therefore, we developed a a new axle detection system using laser rangefinder sensors that measure distance by beaming light at high frequency. While the network rail engineers were working on site installing permanent power, we used this opportunity to install our sensors. The axle detectors are installed at the entrance and exit of the bridge, basically pointing to the railway tracks. And when an axle crosses the sensor location, it cuts the laser, and this feature is used as a mean for identifying the presence of axles. The figure below shows a typical output from a rangefinder. In addition to the axle detection system, we also installed some high-grade accelerometers at the support locations. The output from an accelerometer will be used to measure deck rotations and eventually obtain the support fixes. This is a very short summary of the system we are developing, and my colleague Dr. Miguel Bravo Haro will describe the software architecture of the digital twin system in detail. Thank you very much for your attention. If you have any questions, please do not hesitate to contact me over the email, and I will be delighted to answer them. Thank you.